Okay, good morning. Good morning, my dear students. Good morning. Nice to meet you today. Very good. I will start today class, right? Today discussion we will see. Today, what I am going to do, last class I just started this one, isn't it? Design of short column with the movement, right? Some this theory and all we have seen. What is the uni-axial bending? What is biaxial bending? And what is the already we have a formula for accidental eccentricity, and then now due to eccentricity in applying load, okay, I told you the edge columns are subject to uniaxial bending while the in a framed build structure, while the corner building columns are subjected to biaxial bending in a framed structure. Okay, due to the application, the eccentricity involved in the application of load, that it can be computed. Okay, M by P that can be computed, right? That is due to load, eccentricity due to load, in addition to the accidental eccentricity. Okay, so I told you the best method is the use of interaction diagrams to analyze or design such columns. We go for interaction diagram. That is the widely used method, extensively used method. I told you, and I said I will tell you some introduction about this interaction diagram. Okay, yeah, that is called PAM. That is axial and bending moment. PM. Okay, PM interaction curve. Okay, when both P and M act on a member, right? When an just I will read out. When an eccentrically loaded column is subjected to P and M, for every load P, there is a particular value of M. All of you listen. For every axial load, there is a particular value of bending moment induced in it. Okay, which will cause failure. That's a combination that will cause failure. Okay, for if the axial force varies, accordingly the additional bending moment required to cause the column failure will be different. Okay, for every load P, there is a particular value of M which cause failure. That alone you can remember it. Okay, thus there will be infinite combinations of P and MU. Thus, there will be infinite combinations of PU and MU. Okay, if the obviously okay, let us see. There will be obviously if the PU is more, less the MU may require. Okay, no, it depends on the eccentricity of loading. It's okay. But however, there's a combination, infinite number of combinations are there between PU and MU with jointly, with the combinedly, by combined action of it, the failure will be caused in the column. Okay, which can safely act together for a given RC section. Okay, there is a infinite number of combinations of PU and MU which can safely act together for a given RC section, or which will cause failure of RC structure. There is a combination of it is involved. The particular value of MU for a given value of PU can be found only by trial and error. Listen, the particular value of MU for the given value of PU. Okay, PU is the ultimate axial load, MU is the ultimate moment. Okay, can be found only by trial and error, and the work is quite tedious, right? That's why it will be more convenient, especially for routine design, to construct a curve showing the PU and MU combination and read of value of MU for a given value of PU or vice versa. If PU is given, you can read the MU, what should be the MU. If MU is given, you can read out what should be PU. Okay, there is a combination already established by carrying out some experimental work in the national laboratory and all. This curve has been constructed. This interaction, PM interaction curve constructed. Okay, that's what it says, right? Such a curve showing the limiting value of PU and MU is called a PM interaction curve, right? So this is the PM interaction curve. Just have a look at this one. Here, we want to use a dimensionless number. Okay, that's what. This can be made non-dimensional by using a diagram such as. I want to make it non-dimensional. For that, what we are doing, P is there, no? In the ordinate, instead of taking P alone, P by FCK-BD. Okay, so FCK-BD, the unit for FCK-BD as well as P, same. So it becomes dimensionless number now. P by FCK-BD in the ordinate. Please remember, in the abscissa, in the x-axis or abscissa, mu by FCK-BD square. Okay, mu divided by FCK-BD square value is taken. This is also non-dimensional. Okay, dimensionless number, right? Because the unit for both the numerator and denominator are the same, get cancelled. So it become non-dimensional, right? the curve is constructed like this. It will look like this. Okay, actually axial load only. If the column fails by axial load, this point, okay, at this point the column fails by axial load alone. In such case, the PU value will be very high. Okay, so axial, it will take more axial load, right? It depends upon the eccentricity of loading. If the eccentricity of loading increases, obviously that PU into eccentricity will give you the MU, moment. Okay, the moment to which the column subjected. If the eccentricity increases, the eccentricity application of load increases, what will happen? What will be the moment? The column will be subject to moment, axial force into eccentricity, P into E. Okay, so moment increases, no. So the failure curve will go like this. Here, compression failure. Still, the predominant action is compression. The column will fail by yielding of material, concrete as well as steel in compression, yielding in compression, called crushing failure. Okay, compression failure, called compression failure, crushing failure, or yielding failure of materials and all, up to this level. After this, what happens? There is a balanced failure. Both are predominant. The failure may occur due to axial force as well as moment. Both balanced manner fails the column. Okay, at this point, that's what shown in this interaction diagram. Here and all up to this. Okay, combination, both are predominant. Here axial action is predominant. Bending is comparatively very less. But when it comes to here, tension failure. Why tension failure? Axial action is less, bending action is more. That is why, since the bending action is more, the phase which is when the column bends like a beam column, okay, what happens? The tension side, the material fails. That's why tension failure. Okay, this much information more than sufficient for you about interaction diagram. So these interaction diagrams are available in SP16. You can refer it and solve any problem, right? That's what. Interaction curves gives the strength envelope for the reinforced concrete section subject to combinations of direct load and bending moment, P and M. We know that. Okay. Point outside the diagram represents failure of the column. Points outside these diagrams represents failure of the column. Combination or inside the diagram are safe. Okay. If inside the diagram, if you get, okay, this if you plot curve, the point, okay, that's the discussion on this way. Only the non-dimensional quantity along x-axis. M by FCK BD square, P by FCK BD. Okay, non-dimensional quantity. Here MU by FCK BD square, here PU by FCK BD we are taking. That alone you remember about interaction diagram. So we will straight away will go to the theory part is more. If you see that Dr. Professor P.C. Varghese textbook, many in the design of column, a lot of theory has been discussed. Okay, but what is there in your syllabus? I have to teach you only column subject to design of column subject to uni-axial bending and design of column subject to biaxial bending. With that, even the circular column has been discussed, and the discussion is lengthy. Have a look. But what is required, that alone I am focusing. Nothing is fixed. No, you can refer any book of your choice because syllabus is there. There are several textbooks available. Earlier, when it was taught and discussed in working stress method approach, several textbooks were available 25 years, 30 years back on RCC. Okay, but in limited state design, limited textbook available like standard book of Professor P.C. Varghese textbook. In India, the book I am talking, and Devdas Menon, Unni-Krishna Pillai textbook of IIT professors of Chennai. But in that, the theory has been discussed much than the problems. Okay, design procedures. But I told you the way of presentation of design procedure is very nice in this Professor P.C. Varghese books because he ruled out a table and done it in a very nice way. That's why I refer this book. Moreover, this book was praised when it was published first time during 1994-93 during my stay at Regional Engineering College Warangal as a faculty member. That time, the book was appreciated by one senior most eminent professor of that institute. Okay, he used to always praise this book like anything. That time in limited state design, Professor P.C. Varghese was the first in okay, after Ashok Jain. This book was become popular. Earlier, there was a book, Ashok Jain book was popular. That was the only Indian author book available when I was doing my graduation. Okay, so I am doing all other discussion with you. It's okay. Interaction curve in SP16. Symmetric arrangement of steel for, okay, Actually, in the interaction curve for rectangular and circular columns with a symmetrical arrangement of steel, in which in that interaction diagram, if you see, that is for symmetrical arrangement of steel in a column. Okay, that alone you keep it in mind. And for different various cover ratio, that is called cover ratio. And for various cover ratio, the symmetrical arrangement of steel for Fe250, Fe415, Fe500. So different diagrams are available for different grades of steel. Not only that, and also for various cover ratio. Cover ratio means D dash by D. Actually, where you provide a steel reinforcement, there is the effective cover available. Okay, that will be given. Effective cover value will be given in the problem itself. That is called cover ratio. Effective cover to lateral dimension ratio. Okay. Now, if it is 0.1, 0.15, 0.2, accordingly you have to refer different charts are given. Charts 27 to 62. So this much charts available. Charts from number 27 to 62 in SP16 interaction. They all are interaction diagram charts. Okay, you have to refer the respective charts based on the given data. You have to refer that suitable chart. Okay, so I have shown here a typical chart which is available in SP16. Okay, in which you can see Fy equal to the grade of steel. This cover ratio I told you, the effective cover to lateral dimension ratio. That is called cover ratio for 0.1, and how the arrangement. Okay, the steel will be arranged all around. Why? In which case you have to go for all around if it is subject to biaxial bending. If the column is subject to biaxial bending, the steel has to be provided all around, even here also, all around. But the column is subject to uni-axial bending, na, this much passion you have to provide steel only here and here. This is D dash. Okay, this is the effective cover is D dash. This cover is important. This will be definitely more than 50 mm. Okay, normally the clear cover required is 40 mm only in column, but this will be 50 mm, 55 mm, 60 mm like that. D dash. See here, D dash is shown here. Okay, the longer dimension you have to take it as capital D, the shorter one as in a rectangular column B. Okay, so this way, area of steel is equal to PBD by 100. What it means? Percentage of steel. Percentage of steel means P by 100 into BD. Okay, so if you want to compute the area of steel, because you will be obtaining only the percentage of steel required, so percentage of steel by 100 into BD. Okay, so this is axis of bending. This is the axis of bending for such a column, right? So all the such details are given. This is the curve. In this curve, see here, PU by FCK BD, MU by FCK BD, the values are given. Okay, the 0.1, 0.2, 0.3, 0.4. Likewise, MU by FCK BD square values are given, and then PU by FCK BD values are given as from 0.1 to 1.1, even 1.3. Up to that, it is given. And on this curve, there are so many curves. Okay, not only a single curve, so many curves. Addition to that, it is written percentage of steel divided by FCK is equal to 0.26. Okay, percentage of steel divided by FCK 0. Percentage of steel divided by FCK 0.02, 0.04, 0.96, 0.08. In this curve is for 0.08. This curve is for 0.1. Okay, so percentage of steel divided by FCK equal to 0.25. Likewise, addition to that, it is written, right? Let us see how to refer this chart. For that, we have to see a problem. For today class, I am going to discuss only uni-axial bending problem. This problem with you. Okay, calculation of steel for a given PU and MU. PU and MU are given. You have to compute the area of steel required. It means design problem. It's a design problem. The column 300 mm by 400 mm, rectangular column, isn't it? Mm has an unsupported length of 3 meter and effective length of 3.6 meter. Effective length is 3.6 meter, unsupported length is 3 meter. It is subject to PU, ultimate axial force, 1100 kilonewton, and MU, 230 kilonewton meter, about the major axis. Okay, why it is called major axis? Actually, in that column, the capital D is there, no more this 400 mm the side, that is called capital D. The axis of bending is the major axis there. Okay, this problem I told you know. So here, this is major axis, right? The depth is more, right? In the bending, when you see bending of this column, the axis here is minor axis. Okay, that you remember. That's what. Right now, you have to calculate slenderness ratio. You have to do certain checks and all. Okay, first calculation of slenderness ratio, whether the given column is a short column or not, that you have to verify. So we know this effective length is given as 3.6 meter, no, 3600 mm. Unsupported length is L equal to 3000 3 meter, that is 3000 mm given. Therefore, slenderness ratio LE, effective length divided by lateral dimension 400, which is lateral dimension. Capital D you have to take, 400 you have to take. Why? The bending is, I know, I hope you will understand. You have to refer this chart figure. The bending is this direction. Okay, this is 400, this is 300. B is 300, D is 400. So the bending is this side. Okay, this is the axis of bending. That is why this 400 you have to take to calculate. Always okay. That's what, right? Which is 9. Even if you take least lateral dimension 300 also, it will be less than that. Okay, short column, the axis of bending with respect to axis of bending. Okay, 9. We got it. And then accidental extents involved also, you have to check just. Okay, because there's a formula available. Let us check without considering loading. Okay, without considering loading for a given column, just we are examining the given column is short, and both slenderness consideration as well as accidental eccentricity consideration also we are verifying. E minimum equal to L by 500. I told you the Codal provision, the formula, plus D by 30 is equal to unsupported length 3000. It's not effective length, unsupported length. Divided by 500 plus D. D is 400 here. Divided by 30, so 19.3. Okay, it's short only. The given column is short, and the accidental eccentricity involved also lesser within the limit, because the accidental eccentricity should not exceed 5% of the lateral dimension. Okay, 5% means 0.05 D. Other words, D by 20. 1 by 20 is nothing but 0.05. That only written this way. Okay, 5% means 0.05 D. Otherwise, D by 20 is equal to 400 by 20 is equal to 20 mm. Okay, so this is within the 21. Okay, with that nothing else. So the design accidental eccentricity will not involve. That will not cause any moment, because the accidental eccentricity is within the limit 20 mm. Okay, so next we are going for the eccentricity involved due to loads, application of loads. Okay, calculation of certain parameters we are doing. Actually, M by PU, MU by PU is equal to, that is the eccentricity of application of load. Okay, is equal to the M is given 230 to the power of 6 Newton mm, because 230 kilonewton meter given into 10 to the power of 6 Newton mm divided by P is 1100 kilonewton in 10 to the power of 3 Newton converted. So you are getting 209 mm, which is much higher than 20 mm. So design for MU. Okay. So see, the load is applied with this much eccentricity. So it's not within 20 mm. If it is within 20 mm, you need not design for moment. Okay, you can design only for axial load. Formula short column with axial load alone sufficient. But it is more than 209. Okay, that is why you have to go for the interaction diagram. For both axial load and moment, it has to be designed, right? So you have to calculate certain parameters. So what parameters required to refer interaction diagram? PU by FCK BD, this parameter required. That is computed. PU is given 1100 Newton converted divided by FCK is given as 25 Newton per square, M25 grade concrete. Okay, into B is given as 30, D is 400. Okay, equal to 0.37. Next, another parameter you have to calculate. Okay, that is MU by FCK BD square. Calculate it to refer interaction diagram. These are the, this is in ordinate, this is in abscissa, no, in that interaction diagram. That's why you have to calculate this unknown parameter. All are given data, so you have to calculate it. MU by FCK BD square. MU is given as 230 kilonewton meter. To convert it into Newton mm, 10 to the power of 6 divided by FCK is given as 25 Newton per square into B is 300 mm, D is 400 mm square is equal to 0.19. Okay, and also this cover ratio D dash by D is equal to the cover also given in this problem. Okay, what is that? Cover is given? No, it's not given. Just see, yeah, D dash, assume D dash equal to 60 mm given. If it is not given, you have to take it as 50 mm. Remember, all of you. If this cover is not missing, you have to assume it suitably. Normally, it will be 50 mm. So 0.15. Okay, you are getting 0.15. Suppose you are 50 mm, you are assuming it's not given. Say it comes 0.1 0.3, 5 or 0.14, take it as 0.15. Okay, remember. Now, amount of steel required, right? We have come to calculation of steel. Otherwise, amount of steel required. The title you can change suitably. Calculation of compression steel. You can write calculation of steel, compression steel. Okay. So for that, you have to refer the interaction diagram. Please remember this two parameter. You have to refer the interaction diagram for Fe415 steel and D dash by D ratio 0.15. That respective curve you have to refer. This two parameter value you remember. Okay, I will come. Right. This is the interaction diagram available in SP16. Which diagram shall I refer? This is for FY415 steel. Here 250 steels and all there. This is FY250. Don't refer this. Okay. Here also D by D ratio 0.1, 0.15 and all there. Don't mistakenly refer. Okay. This is for FY250 steel. You have to come here. It is given a nice color picture. Okay. So FY415 steel, D dash by D ratio is 0.05 only. No, this is not required for us. This is D by D ratio 0.1. No, our cover ratio is 0.15. So go to that other diagram. It's okay. This is 0.15. So this cover ratio is 0.15. FO is 450. So this diagram we have to verify. Okay. Now I have come to that. Now go to that value. What is the value here? This ratio PU by FCK is 0.37. Okay, 0.37 where it is 0.2, 0.3, 0.4. Okay, this is 0.32, 0.34, 0.36, 0.37 in between these two. Remember, below 0.4, one leave middle. Okay, in this middle it is there. Keep it in mind. It is here. Okay, we have to refer here. Okay, what is other value? Other value is MABFC is 0.19. Okay, 0.19. I told you no here. Here you have to refer. Okay, remember here 0.19. This is 0.1. This is 0.2. 0.19 means this one. So go above that. Okay, go further. Go. So here I have to refer. I told you no. So here 0.19 no. What is that? 0.2, 0.19. I think I am right. Okay. So let me check 0.19. Yeah, it comes here. It comes somewhere here. What is that? 0.16. Okay, somewhere here it comes. Somewhere here I am getting. For this value, no, is it 2? No, 2. I see here. I'm sorry. This is 9. Okay. In between 0.14 and 0.16. Okay. See here this value. See the curve. Okay. 0.14, 0.16. Which one? Percentage of steel divided by FCK value. P by FCK value. Please listen here. Between 0.14, 0.16, I got it. Okay. This one, P by FCK value. So it comes around 0.15 approximately. Okay. So I think it's 0.15. Yeah, it's 0.15. Very good. No. Where is that? 0.15. It's 0.15. P by FCK value is found to be 0.15. Mistakenly, if you take 0.16, it doesn't matter. No problem. 0.15 or 0.155 or 0.16, anything. Okay. But exactly it comes in for this problem 0.15. Therefore, P by FCK we got. Percentage of steel required divided by FCK is equal to 0.15 we got from interaction diagram. Therefore, percentage of steel is equal to this into FCK. Okay, it is in the denominator. No, just take it the other side here. So the percentage of steel P is equal to 0.15 into FCK, which is 25. Substitute 3.75%. Okay, so it is in between 0.6 to 8%. The minimum reinforcement should be 0.6. No, maximum not 8, not more than 8. 3.75 lies in between. Okay, 3.75% is the percentage of steel required. Therefore, the area of steel required equal to percentage of steel means what? P by 100. Okay, 3.75 divided by 100 into BD. 3 into 100 into 400, which is equal to 4,500 mm square. That is missing here. Okay, 4,500 mm square area of steel required. Okay, so the author has decided to provide first. You have to think and try. Suppose you are using 20 mm, you want to use 20 mm. It's a column, no? Normally in column we will be using 16 mm dia bar, 20 mm dia bar, and 25 mm dia bar, 28 mm dia bar, okay, 32 mm dia bar, like that. So 16, if you suppose you are deciding what diameter of bar to be used. Okay, you are, for example, you are taking 16. You are trying area of one bar. Okay, 4,500 by area of one bar you are putting. It comes around 18 number. Okay, 19 na 99. Okay, is it possible to accommodate 9 bar, because only 300 mm available in that column? Okay, it's a 300 by 400 column. I cannot accommodate this side 9 bars, that side 9 bars. No, 16 bar I cannot go. So next time I'm just thinking, is common sense. 20 bar. 20 bar I'm doing, I am coming around, getting around 15. Okay, some 88 this side, that side. No, I cannot accommodate. Then I am going for 25 bar. 25 bar I am getting around 10 number of bars. Okay, so this side 5, that side 5. It may possible to accommodate, but with the clear spacing between the bars should not be less than. Hope you will remember the quarter provision. Nominal size of aggregate used in concrete plus 5 mm. The maximum nominal size of aggregate used in concrete is 20 mm aggregate plus 5 mm, 25 mm. So the spacing between the bars should not be less than 25 mm. Okay. Keeping all these things in mind, you have to decide what diameter bar to be used. Finally, we found 28 mm dia bar. If I use only totally 8 number of bars required, this side 4 bars, that side 4 bars I can provide. So the author has decided. You write some designation. 4T. I already told you. Don't write it this way. 28T means 28 tar steel. Some people use some circle and some T to represent tar steel. One circle over which a T will be drawn to represent tar steel. In this book, the author has used only capital T to represent tar steel. Okay, 28 T dash 4 numbers on each side you write. First you write dash 8 numbers, then you write provide 28T 4 numbers on each side. It means what? Totally 8 numbers of 20 mm dia bar required. Okay, so you have to provide here 4, this side 4, totally 8 bars, right? Now you have to examine this one. How do you examine the spacing? Either you can examine the clear spacing, or center to center spacing also you can verify. How do you verify? Please see here, in this direction, here the clear cover supposed to be 40 mm. Here the clear cover supposed to be 40 mm. Totally 40 into 40, sorry, 40 plus 40, 80 mm. 80 mm, this side half diameter of bar, that side half diameter of bar. Okay, 28. Add with 80, 28, 108. Okay, in 300 you deduct 108. That divided by how many spacings are there in between? 1, 2, 3. Divided by 3 will give you the center to center distance between this bar approximately. May not be clear spacing. Okay, spacing of bars you will be getting. That's what, right? So it is shown here in this problem where it is. Just now I told you, right? That's what. Spacing of steel. You have to check it. 300 minus 108. How? 300 minus, see here, in this column, here only 60 cover to the main reinforcement. The reinforcement is provided symmetrically on both sides, not all around, both sides. Here it is 60 effective spacing. But here the clear cover normal to a column 40 only. Okay, 40 plus 40, add off 28, off 28, 128. Okay, that is this side half of 28, this side half of 28. So totally 28. So 40 plus 40, 80 plus 28, 108. Okay, so with the 300, this 300 mm, no, deduct 108. That will be 3, will give you the spacing between the bar. Okay, that's what the author has done. See here, 300 minus 108 divided by 3, 64 mm. It is less than 300 mm. The spacing between the bars should not exceed. Definitely it will not be exceed. It is less than 300 mm. But you have to show. You have done, you checked everything, all quarter provision, you have verified that you have to show in your computation. Less than 300 mm. Okay. And the clear spacing, the spacing between the bars should not be less than So no, that's why it should be more than. It is more than aggregate size plus 5 mm. That is 25 mm. No, aggregate size is 25 mm. 25 mm. So the 64 is more than 25 mm, less than 300 mm. Hence, okay. Okay. Hence, okay. You are right. Hence, okay. Right. Next, ties. Design of ties. How to design ties? Dia link not less than product provision. Now you have to provide ties in your column. No. So the dia link not should not be less than 1/4 of the diameter of the bar used. 28 by 4, how much? Around 7 mm. Okay. Or 6 mm. It is given in the codal. Okay. So the diameter of the bar used should be more than 6 mm or 1/4 of the diameter of the steel, which comes 7 mm. It should be more than 7 mm. So use 10 mm dia stirrup, sorry, that ties. Okay. Cross ties, lateral ties. Okay. So spacing not less than, the spacing should not be less than least of the following. Okay. Lesser. The spacing should not be less than the following. Means what? Lateral dimension 400 mm, 16 times diameter of the bar, which comes 448 mm, and 300 mm. So obviously among this 300 mm is the lesser one. Okay. So adopt 300 mm spacing, right? Use 10 mm dia stirrups and provided it at a 300 mm spacing. So if you don't like, even you can use 8 mm bar. Why 10 mm? Why not 8 mm? Because see the main steel. The main steel diameter is 28 mm dia. It is okay. When compared to that main steel 28 mm dia, it is advisable to use 10 mm dia laterals. If the main steel diameter is 16 mm only or 20 mm only, now you can use 8 mm lateral ties. Okay, but since the main steels are 28 mm, 32 mm, na, it is better you can use 10 mm or 12 mm even ties, even 10 mm tie, lateral ties, you can use it. Okay, with this, the problem, uni-axial bending problem is done, design problem is done. The next class, I will discuss with you this one. Which one? Biaxial bending. Okay, for that there is a special procedure available, Bressler method. Okay, biaxial bending. I will do it in the next class. Today, uni-axial bending is over. One problem I have done. Okay, so with this, I will stop today class. Just I want to record your names. Okay, I know some of you are attending implant training. Those who are attending implant training are not in a position to attend class. However, I am happy to see at least this much strength today. Okay, and I also understand that some placement activities are also going for you in online, isn't it? It's okay, no problem. Just I want to record your names. Okay, so the names of the students attending the classes have been recorded, right? It has been recorded. Very good. So I will stop today class. Bye to all of you. If you want to discuss anything, we will discuss. Okay. So stop recording first.